Hello everyone, welcome back to the series of Database Internal. In last few videos, we already have learned about what is transaction and its acid properties. But the question is, how does database ensures atomicity and durability? We have learned that database ensures data integrity, consistency, atomicity and durability. But database must be doing something internally or must be having some algorithm so that it is ensuring even during the transaction if crash happened, if database crashes or something went wrong between the transaction while transaction was in progress, it undoes those operations to make database atomic, and it ensures once a transaction is committed the changes are made permanently on the hard disk. But how does database does that, right? The question is, how does database ensures atomicity, data integrity, consistency and durability? The answer to this is very simple. There is a concept called as write ahead logging. Database uses write ahead logging to solve this problem. Before directly jumping onto the write ahead logging, we will first talk about some of the basic and fundamental concepts to understand the trade-offs that lead us to the solution called as write ahead logging. So we will not directly jump onto the what exactly is write ahead logging. Instead, we will first learn from very first step, or you can say from first principle, that how we came to this conclusion that write ahead logging will solve this problem, can ensure durability, atomicity, consistency, data integrity. All these things can be solved using write ahead logging. So the agenda is very simple. We will start with understanding the problem statements. What exactly is problem with like writing continuously on the disk, understanding some of the basic and fundamental concept like the flow between when client fires the query and it goes through database server and what happens internally on the database server. Then we are going to look at various storage options like we have CPU cache, RAM and hard disk, or you can say that some permanent storage. Then data is stored in pages, which is fixed number of blocks where data files are written. Then we will also learn about what is extents, and then we will see the problem and possible solution from the first principle and trade-off between like various storage options. And then we will come to our requirement. So basically, we build a solution. There is a problem that exists. We build a requirement, right? That okay, these are our requirement. Like we must have a crash recovery system where we can undo and redo the operation. We must optimize the disk IO, and we will talk about like batching, caches and async writes, and then we will like understand like the transaction should be atomic and it should be easier to manage concurrency, right? Then we will look at database policies. Like there are some database policies that exist through which we can decide like how we transfer data between RAM's IO buffer to the disk, or we can load data from disk to RAM's IO buffer. And then finally we will come to write ahead logging, where we will start with explanation, log structure, checkpoint, and then we'll talk about point in time recovery. Once we understand all these concepts, you will have a clear knowledge of what exactly is write ahead logging, how it came into the picture, what are the trade-offs. And when I'm talking about write ahead logging, I'll tell you I'm not talking about a specific database. I'm more talking about the concept, and this concept doesn't only apply on databases. A lot of other solutions also implement write ahead logging to achieve lower latency and like disk optimization. We will see that in action for sure. But before that, let's jump on to the very first thing, understanding the problem. So we will start with same example of transferring money from one account to another account. Alice is sending $50 to John. Let's call this transaction T1. Alice has initial balance of $700 and John has initial balance of $100. After the transaction, John's balance should be $150 and Alice's balance should be $650, right? Let's look at the same query that we have seen in last few videos. I have annotated the query in this orange annotation, where query 1 represents a select query where we are selecting the balance of Alice account, and then we are updating Alice account in query 2 by decrementing that $50 and adding that $50 to John's account, that is query 3. Going ahead, I'll call this SQL statements as query 1, query 2 and query 3. So this is basically a transactional query where we are beginning the transaction and committing the transaction. There are 3 queries inside this begin and commit transaction. Now look at the problem statements that we are trying to solve. If you look closely, we are starting the transaction and we are committing the transaction. In between start and begin transaction, we have 3 query 1, query 2, query 3. But in between the transaction, the database server went down. The 2 query went successful, query 1, query 2. While query 3 was in progress, database server went down. Now this is violation of atomicity, because atomicity says that either all or nothing. It means either all the queries should be successful or none of them should be successful. But here if you see there are partial completion of queries and query third failed. This is violating the nature of transactional query, right? So database ensures that transactions are atomic in nature. This is problem 1, that how will database internally implement the solution where we can guarantee that these transactions are atomic in nature. Even though the database server itself went down, whenever it comes up, it should either undo all the operations or complete the query 3. Right? We will definitely go to the solution. Now let's go to problem statement 2. This is problem statement 2. So basically there are 3 queries, query 1, query 2, query 3. We are beginning the transaction, we are committing the transaction, and all 3 query went successful. But just after committing the transaction, when database was trying to flush everything from in-memory to permanent storage, the database server went down. How database will ensure that once a transaction is committed and signal is sent to the user or client that transaction was successful, the changes are never lost. If you look closely, the changes are done over here from $700 to $650, from $100 to $150. So Alice has successfully transferred $50 to John's account. So there are 2 problem statements for now that we are seeing. The first is atomicity, the second is durability. Even if something goes wrong in between the transaction, database server has to ensure that whatever was done successfully in that transaction should be rolled back, right? And if something has been committed, database needs to ensure that the changes after committing a transaction must be flushed to the permanent disk. Even in case of disk failure or disk get corrupted, that data should not be lost, right? We will talk about that scenario as well. Now we have 2 problem statements. One is atomicity and durability. And even in case of database server failure or system failure or something went wrong exceptionally, we should ensure these 2 properties, right? So we need to have something internally implemented to solve this problem. To solve this problem, first we need to understand the flow of the query execution, right? How data gets transferred within the system, or how client sends the data to database server, and what happens internally. So before solving the problem, let's see some of the internal component, and then we can utilize these components to solve our problem. So basically there is a client and there is a database server, right? Suppose this is the transaction. Let me zoom in a bit. Suppose this is the transaction where we are beginning this transaction, right? And there are 3 statements, A, B and C. And then we are committing this transaction, right? Client is sending this query to database server. This database server will have multiple components, CPU, RAM and a permanent storage. So basically whatever is there on CPU and RAM is volatile. When I say volatile, it means when there is a power outage or there is a power loss, all this data will be lost. So the very first thing, whatever is coming and whatever is committed, somehow we need to write it into the non-volatile storage, or you can say permanent storage, or you can say hard disk or SSD, right? Now let's look closely. If you look closely, this CPU has something called as cache. So CPU has multiple level of caches, L1 cache, L2 cache, L3 cache. Whatever is stored over here in L1, L2 or L3 cache can be accessed very quickly. So the fastest way to access the data is CPU cache. But the problem with CPU cache is the size of the CPU cache is very less, in just few MBs. So we cannot store very large data in CPU cache. Only very frequently accessed data we can keep in CPU cache. Also, CPU cache is volatile in nature. After CPU, the next storage option is RAM. RAM is a bit slower than CPU but a lot faster than hard disk. RAM has a specific reason called as IO buffer. When we load our data from hard disk, we actually load pages from the hard disk. Pages is the fundamental unit of storage. which is fixed size of blocks, and each page ranges from 4 KB to 16 KB. Basically, your data gets stored inside this page, and each page can contain multiple rows, but those rows gets divided between different pages. Now these pages resides inside hard disk or SSD, you can say permanent storage, and your data gets divided between many pages, and these pages are stored at different locations. Now different database has different implementation. Some of the database can keep the size of one page as 4 KB, and it ranges from 4 KB to 16 KB, right? So basically CPU process this statement and then it execute that statement using RAM. Your statement A, B, C can change any of these pages, right? So let's say A and B change page 1 and C got written in page 3. Then page 1 and page 3 will get flushed into permanent storage, right? And then there comes hard disk. Writing data on hard disk is much slower than RAM or CPU. We need disk IO operation to write data onto the hard disk, and disk IO operations are very costly. Let's look at why disk IO operations are costly. I will not go into the deeper explanation of why disk IO operations are costly, but here are some of the points. You can pause the video and look at why disk IO operations are costly. Since this video is completely focused on write ahead logging, I will not spend much time on the operating system concepts. That's why I have written down some of the points. You can pause the screen and look at these points why disk IO operations are costly. Now let's come back to this diagram again. So the very first problem that we are seeing over here is disk IO operations. We want to optimize disk IO operations, right? So the very first requirement is when we are saving any data to hard disk or permanent storage, somehow or there should be some way to optimize disk IO operation, because writing every data, every statement to hard disk is not an optimal solution, right? We want to optimize this disk IO operation. We do not want every changes that are coming, we directly write it into the hard disk. That way the latency will be very high, right? Also, what if there is a power outage, there is a crash happen? In that case, we will lose our data. There is no way to recover the data. So let's write it down somewhere, right? So let's write it down. So the first requirement is nothing but optimize disk IO, right? Second is recovery. This is nothing but crash recovery, right? Crash recovery. What is the third thing? If you do a lot of disk IO operation, obviously the latency will be higher. That means performance. We need to optimize our database for good performance, right? Then the third thing that we are looking for is performance, and we will solve all of these problem basically. Like we will optimize the disk IO, crash recovery, performance using write ahead logging. Okay, now we have seen the various storage options. On a quick note, these are the volatile storages, CPU and RAM, and this is non-volatile storage. We need to write everything onto the permanent storage using disk IO operations. And what is disk IO operation? Disk IO operation is nothing but transferring data between RAM and hard disk. So sometimes we write our pages using disk IO operation to hard disk, and sometimes we load these pages using disk IO operation to RAM's IO buffer. And this is our requirement. Basically, we do not want continuous disk IO operations. We do not want to write everything directly on the hard disk. Somehow we need to use this level of cache. Sometimes very frequently data can be kept at CPU cache, right? That way we will be able to optimize the performance, because reading data from RAM and CPU cache is much faster than hard disk or SSD. Now you can argue that we are writing everything on hard disk. What if that hard disk get corrupted? And that's a valid point. That's why there is something called as RAID. So we configure our hard disk with multiple hard disk and SSDs in place with RAID configuration. And RAID is nothing but redundant array of independent disks. Basically what it does is it keeps the backup copy of the data on multiple disks, and that way we will have replica of those data, and there are multiple ways to solve it. So basically we will make it a stable storage. In a way we will store our data into the cloud. We keep a backup or copy of the data at multiple places, and this will be a stable storage. So even in case of this hard disk failure, we are not losing our data, right? What can be the next requirement? So we have seen in previous few problems, right? We want this transaction to be atomic. So it should support atomicity. What was the second problem? Is nothing but durable. So our transaction should be durable in nature, right? So these are all requirements. When I say crash recovery, we should be able to undo or redo any operation. So these are basic requirements for which we are trying to build a solution, right? Now you must be thinking, what is the structure of the page? How the data looks like inside the pages, right? Let's quickly look at the structure of the page. Let me zoom in a bit and look at this diagram. So these fixed size of blocks are nothing but pages, and each page ranges from 4 KB to 16 KB, and we store our data inside non-volatile storage in form of pages. If I talk specifically about Microsoft SQL Server, these pages gets stored in following structure. We have a page header, then we have data row 1, data row 2, data row 3, and up to n. So basically in Microsoft, one page is of 8 KB, and there is a free space that we keep for keeping our row offset, and these continuous 8 pages are kept together called as extent. So I am specifically talking about Microsoft SQL Server, but more or less every database, or you can say relational database, uses similar concept. There will be fewer changes here and there, but if you know the fundamental of how the page structure look like, you understand basically the concept. That's why I do not want to talk more about a specific database, but I want to talk about the concepts. So what is page? Page is a fixed size of block which ranges from 4 KB to 16 KB. In different database there is different implementation, and each table has row, right? Those row gets stored inside this page. So basically we cannot store all the rows in one page, so we split our row into multiple pages based on the implementation of databases. And whenever we select a row, or you can say when we retrieve data, it is not that row that comes into the memory. Even you are selecting single row, the whole page in which that row resides will come into that memory. When I say memory, I am talking about IO buffer inside RAM. Now we know what is page. Let's go back to the explanation. Let's look quickly what are the problems that we were solving. First is atomicity, second is durability. Then we came to this diagram where we made our requirement clear to build a solution for this problem, right? Where we want optimized disk IO, where we can optimize the disk IO by say batching. So okay, when I say batching, there can be multiple pages that are dirty. When I say dirty, those pages get changes and needs to be flushed using disk IO operation to hard disk. So instead of flushing every page on every SQL command or every write query, maybe I would want that to be flushed over a period of time. We can batch those pages and flush it into the hard disk. And there are algorithms to understand like how we can flush our data from RAM's IO buffer to hard disk. And that is nothing but explained in this diagram. So let's understand what is steal and force policy. So basically there are 4 policies which defines the behavior and the way we flush our data from IO buffer to hard disk. So let's look quickly all these 4 policies. First policy is nothing but steal. Then we have no steal. Similarly, second policy is force and no force. So there are 4 kind of policies over here. In databases, we use combination of any two. One from steal and no steal, and one from force and no force. Let's look at this diagram to understand it in greater detail. Okay, let's say we have this transaction where there are 4 statements A, B, C and D. We are beginning this transaction and we are committing this transaction. Now when a transaction gets executed, let's say query A is successful, query B is successful, and A and B is written in the IO buffer. Can we write this uncommitted data, since like C and D is still there and the data is not committed yet? Can we write A and B, since A and B is already written? Can we write this data or flush this data onto permanent storage? It depends on policy. So if we configure our algorithm using steal policy, then yes, steal policy says we can write even uncommitted data onto permanent storage from RAM's IO buffer. That's why you can see this line over here. Then what is no steal? No steal is simply we cannot write uncommitted data into permanent storage. So no steal guarantees the data that gets flushed from RAM to hard disk must be committed. So no steal do not flush dirty pages to hard disk. Then what is force? Force says at any point of time, we can force that data to be flushed to hard disk, and no force is opposite to this. And no force says there is no burden to flush the data from IO buffer to hard disk. You can do this according to your convenience. Okay, understood? But what is the best policy? So different databases has different requirements, but the solution that we are trying to build here is, if you can see, we were looking for performance, right? So is it a good idea to choose force? Because force will flush everything. As soon as even a single statement is executed, it will forcefully flush that into hard disk. That is nothing but writing every statement even before commit to hard disk. If you want to achieve performance, is it a good idea? No, right? In that case, we will choose no force. Similarly, we do not want to lose our data, right? So should we wait for that data to be committed and then flush it on the disk? No, right? In that case, we will steal that page. So basically, if there is a page which is already written on the hard disk, steal algorithm says we will kick that page out of IO buffer and load our page from the hard disk, change the data, and we can flush that data even before commit. Now you might be having some kind of confusion between like steal force and no steal no force. I would highly recommend do some own research of yourself, because in one video it is very difficult for you to understand everything. Either watch this video twice, thrice, then you will get the point. But for now, to solve our problem, we are going with steal and no force. So when you say steal and no force, what does that mean? Let's come back to the diagram. I want a great performance system, right, which solve our latency problem, which talks about the optimization of disk IO operation. Right? So steal and no force says that we can flush even uncommitted data into the hard disk, but there is no hurry to flush that data, because we are not forced to flush every dirty page as soon as there is a change inside that page. Instead, we can wait for that IO buffer to get fully utilized, and then we can batch our data and process it in batches. In that way, not only we are optimizing the disk IO operation, but we are also doing it asynchronously, and writing data on this IO buffer is much faster. Right? Now doing it synchronously, asynchronously is something that depends on database implementation. There is no wrong or right solution. We always have a requirement. According to that, we build our solution. So steal says that we can even commit uncommitted changes, but there is no hurry to flush that change, because we choose the combination of steal and no force. No force says that there is no hurry to flush your data as soon as there is a change in the page on IO buffer. You can batch it and write the data asynchronously. Okay, at this point of time, there might be some confusion. Let's wait for a minute or two. You will have a clear picture what we are talking about. So our solution is nothing but steal and no force. But still, we have not solved the problem of atomicity and durability. Now let's jump onto the solution of write-ahead logging. Before that, I just want to highlight one note over here, which is nothing but ARIES, which stands for Algorithm for Recovery and Isolation Exploiting Semantics. It says basically it is a specific and widely used algorithm that implements the WAL principle. It's more advanced and detailed approach to database recovery. So where does write-ahead logging come from is basically it's the implementation inside ARIES. Now let's jump onto the write-ahead logging. What is write-ahead logging? So basically we have seen multiple issues. We want to optimize disk IO. We want to have a mechanism of recovering the data. Like in case of crash, we want to recover data by redoing or undoing the operation, right? How we can do that? So write-ahead logging is nothing but it is a way to have a recovery mechanism in case of power outage or crash happens. It supports atomicity, durability, and consistency. Now let's not talk about in abstract way. Let's talk about what exactly is write-ahead logging. I do not want this bookish definition. You can just pause the screen and read this definition out. Let's quickly look at this diagram and understand what is write-ahead logging. So we have volatile storage, we have non-volatile storage. We want to utilize volatile storage for writing or reading data and keeping as much data as possible for our particular server to read from in the RAM or CPU cache, right? For now, I'm just talking about the RAM's IO buffer because this is what this whole process is about, like optimizing the disk IO operation. Let's say we have a transaction T1. We are beginning this transaction and committing this transaction, and we have a value inside a page called A is equals to 1, and I want to change this value. So what happens is this transaction T1 wants to read A. Suppose at that time this page was not in IO buffer. The value of A was not in IO buffer. It loads that value into IO buffer. Let's say the value was 1. Okay. Now it is writing the value. Earlier the value was A is equals to 1. It is writing the value A equals to 2. Instead of writing directly inside hard disk page, what it will do is it will use something called as log file or wall mechanism, write ahead logging. So basically this log file is nothing but append only file where all the transaction changes are appended into a log file sequentially, and then it changes the data here in IO buffer. So data will get changes into this page as A equals to 2, and then it commits the data. Now flushing this data to permanent storage can be done later point of time, or you can say we can write this data asynchronously. Now this was very small example, but this was just to give you a definition of what is write ahead logging. So basically in write ahead logging, we maintain a log file inside secondary storage, and that log file is append only mode. We write those logs in append only mode where we do not write data in between or scattered through multiple pages. So basically when we are writing data on this hard disk, so those data files like for tables and indexes gets written onto the multiple physical locations on that disk, and it changes various data files of the database. And doing even a single operation can cost much more time in compared to this log file where we are just appending the transaction. Still there might be some confusion. We will go to a different example. But before that, let's look at how the write ahead logging or log file structure look like. So let's zoom in a bit. So the log structure is nothing but there will be a LSN, that is log sequence number. So we want to append all the transactions in append mode, right? For that we have a sequential log number. Basically we want to sequence every operation. Why do we do that? This helps us even in concurrency control because we know the sequence of number. In that case we know the latest committed data, and we can optimize our process of concurrency control and manage it in easier way. Now the second thing is transaction ID. Every transaction has an ID, right? Every transaction is associated with a transaction ID. Then operation type. Operation type is nothing but insert operation, update operation, delete operation, mostly write operations, or a signal to commit or begin transaction. Why only write operation is select query do not change anything into the database, so it do not corrupt the data. Then we have a page ID. Page ID is nothing but reference to a page where data should be written, and there is a table ID. So why table ID? Instead we can keep table name, right? So the problem is we want to optimize our log operations as well, because keeping name of the table every time is a redundant operation, right? Instead we can have a number which represents that table name. Then we have a before image. What before image is? It tells how your data look like before that query executed, and how your data look like after that query executed is represented by after image. And then we have a commit marker which says this transaction is committed. Now let's look at this example to understand it. So you must be remembering this image now where Alice is trying to send $50 to John. We have this same transactional query where we are beginning the transaction and committing the transaction and trying to send $50 to John from Alice account to John's account, right? We have one read query, two update query. Let's look at this transactional query, how it will look like when we will use wall, or you can say write ahead logging concept. So let's say a client is trying to execute a transactional statement. The query comes to the CPU, and here is a begin statement and a commit statement. In between we have three queries: query 1, query 2, query 3. One is read query and two is update query to update the balance of both the account, Alice and John. So the very first thing, read statement, right? So we will not log the read statement here, and it also depends on the database implementation, but most of the database do not log read statement inside vol file because there is no use of read statement because it do not changes the data, right? So in that case, basically how the transaction will look like is we will begin the transaction. Operation type is nothing but begin. This is log sequence number and transaction ID is 123. This T1 transaction ID is 123. Okay. Then we come to update query 1 where we want to deduct that $50 from Alice account, right? In that case, our log will look something like this. And again, I'm saying different database has different implementation for same log file. I'm just giving you one example to understand the concept itself. So we have same transaction ID 123, log sequence number 4, 5, 6, 7. So there might be some other transaction going on which is using a sequence number. So you can say from 63 to 67, there are 4 other logs that has been appended on already. Now let's look at this operation. Operation type is update. We are referring to table ID 102, and here also we are referring to the same table, right? Then we are referring to page ID 4242. So what page ID says is the Alice's data inside the page ID 4242. Basically this row 1. So where does this row 1 exist? Inside page ID 4242. It is reference to that. Now before image, look carefully. Let me zoom in a bit so that you will have a greater picture. Before image, Alice's ID is 1 and balance is 700. This is before executing this query. After executing this query, it should deduct the $50 and ID is still 1, right? Now, second update query gets logged as transaction is same. So transaction ID will be same 123. Log sequence number will change. Then operation type is update. Then we have a table ID 102. The same page ID. So basically Alice and John resides in same page. Now before image. So basically John's ID is 3. Initial balance is 100. After the transfer, after image should be $150 because that $50 gets added over here, right? And then we are committing the transaction. We have commit marker over here. Now let's look at the sequence of operation. We looked at a sample log file, how a log will look like inside secondary storage, right? But one question you must be having is we are still writing onto the secondary storage. Then what is difference between writing directly into the data files using disk-IO operation and writing into the write ahead logging? The very simple answer to this is in write ahead logging we are writing sequentially. This log file is append mode only. We are just writing at the end of the file. We always know where to write and it is a sequential log only file. We are not writing anything else. But when we are writing into the database files which are scattered onto different pages and there are multiple database files, there can be multiple database files. It can be an index file, it can be a table file, right? So database maintains different structure. It needs to maintain our indexes. Writing directly into those pages is quite costly as compared to a append only log file, right? And that also we are not doing it very frequently. What we are doing over here is whatever is coming, we are just writing it, appending it into the vol file and loading it into the IO buffer. Once it is written into this log file, then we can say that change is permanent, even though we have not written it into the data files. Because we have that data, we can do it at later point of time. In IO buffer, we will use the two policy that we were talking about, steal and no force. In that way, we will flush our data. Also, we can batch all the dirty pages. So basically, instead of writing everything that is getting executed, we will batch the changes and flush it into the disk. And we will always have this vol file. If something goes wrong or a system crash or power outage, we can always replay this vol file. We will see if a transaction is partially completed, we can undo this operation. So if you look closely, the first problem statement of atomicity, in that this query was failed. So basically we were able to deduct amount from Alice account, but that balance was not credited to John's account. In that case, whenever this database server comes up, it will just undo this operation, and it will only undo in case that file was flushed onto the disk. There is also chances that that file was not flushed onto the disk but is there in the wall file, or you can say log file. Now we have a backup file. So we are only marking, or you can say we are only logging all the transactional statement in the append only file, so that we can have a recovery mechanism. So we can undo the operation. What about redo? Let's say we want to redo something. That is also possible, right? If you look closely, we have this wall structure, we have this log file, right? Now this log file also has something called as timestamp. You want to redo few of the operations, you will see this log file and redo those operations. Now how we have optimized this disk IO operation? Answer 1, we have batched the dirty pages. Second, no force policy, where we are not forcefully flushing every dirty page right away, but we are batching it and flushing it into the hard disk periodically, and that is nothing but checkpoint. So there is something called as checkpoint. We use this term which defines that we flush our data periodically to permanent storage. Okay. What about this wall file? This is growing indefinitely, right? So what we do is, whatever is already written into this disk or data files, or you can say on permanent storage, we archive those entries from the wall file. That's it. And keep a backup of that archive files. Okay. What else we have done to optimize disk IO? We are caching the very frequently accessed pages on the IO buffer. Also, if you look closely, even if you are reading a single row, you are not just reading one row. Wherever that row resides, or in whichever page that row resides, the whole page will come into IO buffer, and with that row some other row might come. So what we have learned so far, let's look quickly. So we already have understood the problem of disk writes, we understood the flow of client to database flow, then various storage options, understanding the trade-off between various storage options, pages, extents. We also understood the problem and the possible solution from the first principle, and also looked at the trade-offs, right? Then we looked at the requirement, crash recovery, undo and redo operations, optimization. We can do async writes, cache the pages, batching, right? Then we are now able to do atomic operation. Concurrency control is much easier because of that log sequence number, right? Then what? We also have learned about steal, no steal, force, no force. Then write ahead logging. We have learned about like what exactly is the write ahead logging, log structure, checkpoint. Now there is just one topic left, that is point in time recovery. So point in time recovery is very simple. Point in time recovery is nothing but what if something goes wrong and you lose all your data on the hard disk, or you can say what if you want to replace some of the data till a particular timestamp, or you want to recover some of the data from one timestamp to other timestamp between two time ranges. All you can do is you can go and read your log files and replay those operations in a way that your database stay consistent. So this is it. This is what write ahead logging is. I hope you understood what is write ahead logging. I tried my best to explain the concept in a way you understand why even write ahead logging. What is the problem, and what is the problem that we are trying to solve. We also understood the fundamental concept, policies, and the trade-off between different concepts. So what we have learned today is write ahead logging basically, right? But I have not talked about database specific concept, but I have talked about in a way that what exactly is write ahead logging, and apart from database there are multiple use cases where write ahead logging is used. I would highly recommend you to go and check out, do some search on Google and find out what all are the use cases for write ahead logging. That's all for this video. I hope you enjoyed this video. Please do not forget to like, comment, subscribe, and do not forget to press the bell icon. Thanks.